I missed recording the first part, but maybe I'll just explain where we're on the problem. Find the volume of a cross section. The volume of a solid. We have cross sections perpendicular to the x-axis between x equals a and x equals b. We use this formula. And the idea is this. In this example, if the cross sections are perpendicular to x-axis and extend between the curve and the xy plane, y equals x, this straight line, and the curve y equals x squared, this parabola between x equals 0 and x equals 1. If I take cross sections perpendicular to x-axis but are squares that have base between those lines, then my formula says a of x, the cross section at any point x, is the length of a side squared. That's the area of a square. But the length of a side is the distance between the curve y equals x and y equals x squared. So it's x minus x squared. So the side squared is x minus x squared, or x to the fourth minus 2x cubed plus x squared. To find the volume of the solid, then I just have to take the integral of the cross-sectional area dx. That's our formula. I didn't need to circle it in again, I guess. And for this particular function, that means you integrate from x equals 0, where the first little tiny square reduces to a point, to the last point where x equals 1, and that's the last cross-section reduces to a point. In between each cross section at the arbitrary point x is x to the fourth minus 2x cubed plus x squared dx. There's the volume. You just have to evaluate that integral. So in calculus 1, you can find an area between two below a curve. In calculus 2, we can find the area between two curves. Now we can do better than that. We can find the volume of a solid whose cross sections are a of x. How about that? So we just have to do this integral, right? Integral x to the fourth is x to the fifth over 5. Remember the power rule? Integral x to the n is x to the n plus 1 over n plus 1. Plus a constant if you want, but remember with the endpoints on here, the constant falls out, so you don't need to put it. Minus twice, integral of x cubed is x to the fourth over 4. Plus integral of x squared is x cubed over 3, again by the power rule. All of these, plug in x equals 1 and plug in x equals 0 and subtract, right? That's how you evaluate these integrals. It's called the fundamental theorem of calculus. To evaluate this integral, you take the antiderivative, plug in the top, plug in the bottom, and take the difference. So I'll plug in 1, and I'll get 1/5 minus twice 1/4 plus 1/3. Right? 1/5, 1 to the fourth, and 1 to the third are all equal to 1. And then I'll subtract each of those at 0. 0 minus 0 plus 0 is 0. That evidently is the volume of the solid. Let's see, 1/5 minus 1/2 plus 1/3. What is that? We're going to put them over common denominator of 30. So I'll say this is 6/30 plus 15/30 plus 10/30 gives me 31/30. How about that? There's the volume of that crazy solid, right? Questions on that one? If that scares you again, well, the rest of these will get easier. But that's the general case for the method of cross sections to evaluate a volume. If cross sections each have area a of x at any point x between x equals a and x equals b, perpendicular to the x-axis, the volume of the solid you generate that way is just the integral of a of x dx, a of x being the cross section. Now, what we'll do is we'll consider some special cases of that. Actually, only 2 of them. As a first special case, suppose that cross sections are washers. I'm sorry, there's discs. What's a disc? Yeah, it's a circle with its interior. An open disc is the interior of the circle. A closed disc is the circle together with its interior. So a disc in any case is the interior of a circle and top of it. Right? Suppose cross sections are discs. Like a circle in its interior. Then what do we get? The cross section formula. And suppose there are discs of radius r of x at each x. Perpendicular to the x-axis again. I won't write that out. The cross sections have area what? Here's where the picture might make it easier. Yeah, it's just the area of a circle. Yeah, awesome. So what you're doing here is you're just taking the special case that the cross sections are circles. Here's the x-axis, here's the y-axis. This is unconventional. The convention is to put x out of the board, y over here, and z up. But for our application, it's easier to put x going to the right and y into the board and z upward. So I'll do that for this class. It's not usually the way you draw it, but it's more convenient here. So if the idea is that if you have this kind of a thing, maybe a horn, you maybe have below this function y equals r of x, a function of x, you revolve each point on the curve around the x-axis. Right? And get a circle, and you take the interior of this thing, so you've got a solid generated by cross sections. And at each cross section, the height of the function is r of x, because it's the function y equals r of x. And I put r of x because it's the radius of the circle. And so what's the cross-sectional area at x? Area of a circle is pi r squared, right? That's your cross-sectional area. Right? It's the area of a circle is pi r squared. So the cross-sectional area is a of x equals pi times r of x squared. So what's the volume? By our formula, it has to be the area of the cross-section integrated, right? And suppose r of x is continuous, then pi times r of x squared is continuous. So we can rewrite this as integral from a to b of pi r of x squared dx. You can pull the pi out if you want. It's just a number, right? That's it. That's the formula for the volume of the cross section when the cross sections are circle or discs, the circle with its interior. And we call that the method of discs. It's the theorem known as the method of discs. And we just derived it from the other definition. It says if r of x is continuous, a continuous function, on an interval, x going from a to b of the x-axis, then the solid, any solid, let's say any solid, you come up with discs as cross-section of radius r of x, perpendicular, this is a symbol for perpendicular, to the x-axis, has volume given by this formula. V equals integral from a to b pi times the radius squared dx. So it's just a special case of the cross-sectional formula where the cross-section is pi r squared for its area. That's the method of discs. Line that. And now you can find some really interesting solid volumes that you'll you know, you can run into an industry and so forth. There's lots of things that have circular cross sections in industry, right? Those are mass produced, you know, pistons in cars and frustrums of aircraft and rockets and so forth. Let's do one of those kind of things. Example, suppose I want to find the volume of the cone that's obtained by revolving the line, by revolving the plane region below the line. Y equals 1 minus a half x for 0 less than or equal to x less than or equal to 2 about the x-axis. Wonder what that volume is. As with all the problems in this sections, it really helps to draw a picture. And this is where those rules I told you last time. How do you draw a line? How do you draw a parabola? How do you draw an absolute value or a 1 over x? Those kind of things all come into play because those are the kind of functions they're going to give you. And if you can draw those, you can revolve them and see what the solid looks like, right? So that's what we're going to do here. This is a line, even though I didn't say so. Why? How do I know it's a line? You can also write it as y equals minus a half x plus 1, and it's y equals mx plus b. It's the slope intercept formula for lines. So I can immediately draw it, x and y, by drawing the y-intercept of 1 and making it slope minus a half. If I go over 1, I gotta go down a half and be right here. If I go over 2, I gotta go down 1 and be right here. It's the line that goes through these 3 points, or just say these 2 points. Right, I could, for instance, I could find the x-intercept. I put x equals 0, and what do I get? I get y equals 1. If I put y equals 0, then I solve this. 0 equals minus a half x plus 2x must be 2. So you plug x equals 0 and find y, plug y equals 0 and find x. And oh, that's just what I have here, this interval. So what I'm talking about is this, I'm revolving the plane region below this, and I mean over the x-axis. Maybe I should spell that out, over the x-axis. And below this line, around the x-axis. So that means I'm going to create a solid like this, and it is in fact a cone, sure enough. Each point revolves around in a circle. And now I'll say at any point x, how can I evaluate this volume? The volume by the method of disks is the integral pi r squared. And I should have put a star up here. This is one of the things you memorize. You also need to put that for the area by cross sections formula. So 2 things to memorize so far tonight. There's going to be 3 in total. Volume is the area from A to B of A of x dx when A is a continuous cross section. That's 1 to memorize. Cross section formula. And then as a special case, this is the method of disks. All right, so there's 2 things to form. I should have started this one. Let's start this one now. We're already past this one. So integral pi r squared from A to B is the formula for disks. The cross sections are disks. What's the area of the disk at x, an arbitrary x? Well, you look at what the radius function is. The radius function is this function, y equals 1 minus a half x, right? So this is your r of x. That's what you're revolving around the x-axis. So I'm going to integrate from x equals 0 here to x equals 2. I was given the interval. Pi times 1 minus a half x squared with respect to x, and that'll give me the volume of this cone. Oh, you got the formula memorized? What you can do is if you leave this an arbitrary radius r, you can actually derive the formula for the volume of a cone using this. So put this more abstractly, don't give a specific line, you leave these A and B arbitrary, and you can derive the formula for the volume of a cone that you see in all the books. So finally, you can prove that formula. Why does that work? You can do it now, right? You can prove it with a little work. That's what he's saying, I think. Awesome. So we have this, it's this integral. So this is, let's see, the integral, we can pull the pi out. Pi times the integral from 0 to 2 of, when we square that, we get 1 minus twice a half x is x plus a quarter x squared. That's what you get when you square that out. And we know how to do these, right? Integral of 1 is x, right? Integral of x is x squared over 2. Again, by the power rule, x to the n is x to the n plus 1 over n plus 1. 1 x squared integrates to x cubed over 3. We're going to plug in 0 and 1 and take the difference. You put a bar here with 0 and 1, or you can put brackets, put still both ways. Plug in the top, plug in the bottom, and subtract. So let's see, if I put in 1, of course I pick easy numbers to plug in. I get pi times 1 minus a half minus a 12. 1 over 4 times 3. And if I plug in 0, I get 0 minus 0 minus 0, so I get 0. So I got pi times 12 twelfths minus 6 twelfths minus 1 12. That's 5 twelfths. I get 5 pi over 12. There's the volume of that cone. How about that? Pretty neat, huh? So you can find volumes of lots of solids of revolution using the method. Yes. Well, just like we did last time, we're going to do it about every section here. We're going to say, well, what's so sacred about revolving around the x-axis? Why can't we revolve around the y-axis? Of course we can, right? It's, nothing sacred about the x-axis. Similarly, if disks have continuous function r of y radius about and are perpendicular at y, at each y, and are perpendicular to the y-axis, between y equals c and y equals d, then the volume of the solid so generated is the integral from c to d, of pi times r of y squared dy. It's the same thing. You just call the axis you're revolving around y instead of x, right? But the picture you might want to draw vertically just for the sake of watching. So now what you're doing, you're saying let y go between c and d, make cross sections that are disks perpendicular to the y-axis, and at arbitrary point y, you take the disk perpendicular here, and you say that if the radius is r of y, a continuous function, so that the area at y is pi times r of y squared, the area of the disk or circle, then this formula applies because it's the same thing, just calling the axis y instead of x and the points c and d instead of a and b. Nothing more than that, right? But sometimes it's useful to see that written down just to realize that fact. So let's try a simple problem. Revolve the same line. Y equals 1 minus a half x between y equals 0 and, oh, I messed this up. This last one up. I'm supposed to go from 0 to 2, and I put it from 0 to 1. My apologies. It's not the cone. Nobody caught me. Maybe they did online. If you're online, you want to cut in, just take the mute off and talk to me. Talk back. Maybe I should fix it right at the end, huh? I came up. Let's do that again just one more time. We could just say it goes from 0 to 1 and say it's the area of that frustum instead, but let's do what we did. It should have been integral from 0 to 2 instead of 0 to 1. The same thing we had, pi times x to the 4, x squared minus x plus a 4 dx, just going from 0 to 2 instead of 0 to 1. And so it would have been pi times x cubed over 3 minus x squared over 2 plus x over 4. Well, that right doesn't look right. And instead of 0 and 1, we'll put 0 and 2. That was a third minus. What did I do wrong here? Something. Oh, I know. No. It's a third.
You're missing out the x to the second on the last one. So it's x squared minus x plus 1/4 x squared.
Oh, yeah, I miswrote that. That's why it was 1 minus x plus a 4th x squared. That's what I did. I miswrote that. There we go. Trying to remember with a formula before. Okay. So this is what we had before. We'll just go from 0 to 2 instead of 0 to 1. And then we get x minus, thank you, x squared over 2 plus x cubed over 12. There we go. And so now we'll get, we should have gotten on that 1 minus a half. 12 12s minus 6 12s is 6 12s. Plus this one makes 7 12s, right? That would have been 1. I still must have wrote it. You guys gotta catch my mistake. If I put in 2, it's 2.
It's gonna simplify to 8 over 12, because those first two terms cancel out.
Yeah, it's gonna be 2 minus 2, and then I'll just get 8 over 12, so it's 2/3 pi, 2 pi over 3. So this should have been the answer. I should have gone from 0 to 2 instead of 0 to 1, and then I get 2 pi over 3 instead of 5 pi over 12. There we go. So there's the first part fixed. My apologies. Now let's do the same curve and revolve it between y equals 0 and y equals 1 about the y-axis. So I'll get a different cone. And I'll use the other formula since it's revolved around the y-axis just for convenience. So this time I take the same line, y equals 1 minus a half x, runs between y equals 0 and y equals 1. And this time I'm going to revolve this way and get a long, fatter cone that looks like this. Right? How do I find the volume of this one? The idea is the same thing as when you revolve around the x-axis. You take the typical cross-section, this time at y, whatever axis you're perpendicular to, and say, what's the radius of this disk? R of y. Well, you have to rewrite x as a function of y instead of y as a function of x. So y equals 1/2 minus a half, 1 minus a half x becomes 1/2 x equals 1 minus y. By subtracting y from each side and adding a half x to each side, it becomes by multiplying by 2, x equals, 1/2 x equals 1 minus y. By adding a half x and subtracting y from each side, it becomes x equals 2 minus 2y. So this curve y equals 1 minus a half x is also the curve x equals 2 minus 2y. That's the radius. The radius at any y, r of y, is 2 minus 2y by writing x as a function of y. That's the trick to this method. And so now the volume of this cone is the integral from y going from 0 to 1, with y where the cross sections begin for y and where the cross sections end for y. Pi times r of y squared dy, right? That's the new formula, since cross sections are perpendicular to the y-axis. So I have to compute this. This is integral from 0 to 1. Pi times the radius is 2 minus 2y. And then I square that and integrate with respect to y. Well, now if pi comes out and I integrate from 0 to 1, I better square this. It's 4 minus 8y plus 4y squared. This time from 0 to 1 is correct, because y goes start cross sections at 0 and ends at 1. So now let's see, integral of 4 is 4y. Integral minus 8y is 8 times y squared over 2, or 4y squared. Integral of 4y squared becomes 4y cubed over 3. Plug in 0 and 1 and take the difference on those. All right, so pi times 4 minus 4, those will go away, plus 4/3 when I plug in 1. I plug in 1 and get 4/3. And then I plug in 0 and I get 0. Evidently, this is 4/3 pi. So there's the cross sections by revolving around the y-axis. You just have to find, to evaluate the volume, you find that radius of the typical cross sections and integrate pi r of y squared dy. How about that? Well, sometimes that's not good enough to have discs. Sometimes the cross sections are washers. So step 3, we'll say if cross sections are not discs, but discs with a hole in the middle, so that they're washers. With outer radius are 2 of x, and inner radius are 1 of x, both continuous. For and perpendicular to the x-axis between x equals a and x equals b, so that you get this kind of a picture. It's very much like the last one, just with a hole in the middle. Suppose I take from A to B a solid like this. Maybe I take a cross section that looks like this, right? And I revolve this around the x-axis, so there's a hole in the middle, right? Maybe it's a piece of a rocket or something, right? But the idea is I take this plane region and I revolve it around the x-axis. I get each cross section is a washer instead of a disc, right? It's a circle taken out within a bigger circle. So at any point x, the cross section is a washer, with inside radius are 1 of x, and outside radius are 2 of x. And if those are both continuous functions, what can we say about the volume of the solid generated? What is the volume of this solid? Well, look, it's cross sections, right? Each cross section is a continuous function. What's the area of the cross section? Each cross section is a washer of inner radius are 1 of x, outer radius are 2 of x. It's like this. So its area is the area of this circle minus the area of this circle. It's pi r 1 of x squared minus pi R2 of x squared. I'm sorry, R2 of x is outside, and R1 is inside. R2 of x squared minus R1 of x squared is also pi times R2 of x squared minus R1 of x squared. Each cross section has area equal to that. So the volume of the solid is what? By the method of cross sections, the volume must be the integral from A to B of the area of a cross section at X, right? We motivated that and defined it that way. And then the area of the cross section, if the cross sections are washers, their area of this is this. And we have derived this formula, which we call the method of washers. This is the formula for finding a volume by the method of washers, and all it is the same cross-section area formula in the special case of washers. So we really only have one formula tonight. It's this one. Volume is the area is the integral of the cross-sectional area. But as important special cases, we have the method of disks, where you replace this with the area of the disk, pi r of x squared, and the method of washers, where we replace a of x with this, pi times outer radius squared minus inner radius squared, because that gives you the cross-sectional area here. So it's really just this formula and two special cases of it. So we'll call that the method of washers. Comments on that one that you want to make? I think the concept is straightforward. Let's see if we can do a problem then. I'm trying to do real simple examples just to illustrate it, and then you can, the hard ones for homework come out. No. The book is pretty good about giving reasonable prompts for homework that are illustrated. Here's an example. Suppose instead of taking a region below a line, I'll take a region between two curves. I revolve, this is the, I think one of the simplest examples. Revolve the plane region between y equals x and y equals x squared, just like we had in that other example, except we made squares, square bases with that. This time we're going to make washer cross sections. Revolve the region between y equals x and y equals x squared about the x-axis to generate a solid. Find its volume. So the picture really helps again. You draw the line y equals x, right? Y equals x. Maybe you already memorized the line, but it's y equals 1 times x plus 0. So it's a line with intercept at the origin and slope 1. It goes right between the axes. Is y equals x. Y equals x squared is the baby parabola everybody memorizes from algebra. It looks like that, right? Let's write down here. Y equals x squared. Put this one up here. Y equals x. And the reason between them then, here's the parabola going off over here, is this right here. Now you revolve that, once you draw the picture and they say, I know what I'm doing now. I'm going to revolve this little plane region around the x-axis like that. And this time I'll get a cone on the outside and a hole in the middle. All right? So it's kind of like a horn. You hollow that out, although you can blow through it, right? But it's got, you revolve this plane region, and here's its image over here, and get a solid with this interior hole. It looks like the cone a cone, except with a hole cut out in the middle. What is the volume of the solid there that I generated? Well, it's like washers. To find the volume, you look at the typical cross section at x. So at any arbitrary x in the middle, I notice the cross sections are a circle on the outside with a circle on the inside cut out. They're washers. right? This is the washer at X with cross sections perpendicular to the x-axis, right? So, what's the volume? It's this formula right here. By the method of washers, I just need the inside radius and the inside radius and the outside radius, so I'm gonna subtract their squares. Washer at X has inside radius what? Well, you look at it, it's this one, right? R1 of X is the height of X squared, it's equal to X squared. Outside radius is the distance up to the line Y equals X, so the outside radius, the revolving, is X, R2 of X. Put it here, R1 of X equals X, outside radius, R2 of X equals X. So the volume by this formula is the integral from A to B, pi times R1 squared, R2 squared, the outside radius squared, minus R1 of X, the inside radius squared, dx. I put in that the cross sections go from here, that's where they start, this is where they finish, this is where you need to be the mathematician and say, oh, I see that if I fill this up with approximating sub-solids, which are sort of thickened rings, what's the idea of the cross section message? They're adding up a limit of the volumes of thickened rings here, all the way down. Here's a thickened ring at the hollow spots in the middle. And anyway, you add up all the volumes, all the rings, take the luminous number, it goes to infinity is the concept. You get the exact volume of this thing. Is the integral of the rings of the washers start at 0 where these intersect, and they end at 1 where they intersect again. If you want to know what those points are, you just set them equal, right? So to find what this point is, you set y equals x and y equals x squared equal. You set x equals x squared, right? By setting y equals x and y equals x squared equal. That becomes equivalently x squared minus x equals 0. And you factor it as x times x minus 1 equals 0. Oh, it's x equals 0 or x equals 1. That's how you find the intersection points. You set these two curves equal, right? So this is going to be the integral from 0 to 1 where the curves intersect over here, where they intersect over here. And pi times the outside radius squared is actually x, not x squared, right? That's the larger radius. This is hard to see, isn't it? Better. Cross section is a washer. The outside radius x, because it goes up to the line y equals x. 2 of x equals x. And inside radius, R1 of x equals x squared because it goes up with the parabola. There we go. All right, so R2 of x, the outside one, is x. I got to square that. Minus the inside one, x squared. Squared. There it is. Outside squared minus inside squared. All I have to do is to evaluate this simple integral. I've got the volume of this rather exotic solid, right? So let's see. Pi comes out, and I integrate x squared and get x cubed over 3. This is x to the 4th, so its integral is x to the 5th over 5. I'll plug in 0 and 1 and take the difference. I've got pi times 1 minus a 5th. That is 4/5 pi. This is x cubed over 3. I messed it all up. X cubed over 3, x to the 5th. 1/3 minus a 5th. Let's see. This is 5/15 minus 3/15 is 2 pi over 15. So there we go. Roughly 6/15. 2/5. Pretty neat, I think. All sorts of things you can do like this. So now, similarly, if cross sections, hate to beat this to death, but the book does this and you gotta try it once. If cross sections are washers perpendicular to the y-axis, there's nothing sacred about x. With continuous outer radius R2 of y and inner radius R1 of y, at each y running from y equals c to y equals d, you get the completely analogous formula. The volume of the solid is what? It's the same formula. Let's draw this picture just so we can see what we're doing. Y goes from C to D. Each cross section is a washer. It's got an inside radius and outside radius. And so there's a hole down the middle. And at each Y, the inside radius is, inside radius is R1 of Y. The outside radius is R2 of Y. And it's the same thing. This was Y instead of X, so you get the same picture. And now Y goes between C and D instead of A and B. You get volume equals integral from C to D, pi times R2 of Y squared minus R1 of Y squared dy. It's just the same formula with Y instead of X and C and D instead of A and B. So it's very easy, but it's just this following trick. In order to do it, you have to write X as a function of Y to get the radius, inside and outside radius. Let's do that same problem again, except with washers the other way. So now example, revolve the same region. The region and the plane between y equals x and y equals x squared, this time about the y-axis. And find the volume. And this is going to again give us washers. It's worthwhile drawing the picture. Here's y equals x again, same as before. Y equals x squared again. The region between is this little slice here, but we're going to revolve it the other way. We're going to make something that looks like this. This symmetric piece over here. And the idea is that each y, this solid has a disc, a washer for a cross section. There's the typical cross section of y. So at each y, what's the inner radius? It's so the function y equals x, so it's R1 of y, the inner radius is y, right? It goes out to x, but x is y. And the outer radius, this is the tricky part on this one, the outer radius, R2 of y is what? You have to write x as a function of y, so x equals y squared is equivalent to, y equals x squared is equivalent to x equals square root of y. So at each y, the radius is this function, square root y. You have to write x as a function of y to get the radii. Now we've got it. The volume of the solid is therefore integral from C to D. Well, the cross section start here at y equals 0, and they go up here to y equals 1. So the integral is still from 0 to 1. It's just now y is going cross sections. And you're thinking of adding up the volumes of all these little rings, thickened rings, and taking the limited number of rings goes to infinity. So you're thinking adding these. That's the mathematician thinking that to kind of double check it. The rings start at 0 and go up to 1. But we have integral from 0 to 1 of pi times the outside radius is the larger one here, y, x equals square root y. So R1, R2 of y squared minus R1 of y squared dy by the Washer's formula for this perpendicular to the y-axis. All right, well, fortunately, this is actually an easier integral than the last one, right? It's lower powers anyway. So this is the integral from 0 to 1, pull the pi out of y minus y squared dy is pi times y squared over 2 minus y cubed over 3, plug in 0, 1, and take the difference. 1/2 minus 1/3 is a 6, so this is pi over 6. Plug in 1, you get 1/2 minus 1/3. Plug in 0, you get nothing. Pi times, which is right at the intermediate step, times 1/2 minus 1/3. Plugging in top and minus at the bottom, 0 over 2 minus 0 over 3. And so you get pi over 6. Good. Well, I burned up enough chalk tonight. I keep going to this drawer. I must be running too fast. That is what I want you to get out of that section, the method of discs and the method of washers. They do have one more kind of problem here, where they revolve the washers about a different line. I think I'll leave that one out, and if you have difficulty in any of the homework, just bring it up and I'll do it in class. And I'll get on to one last topic for tonight. By the way, there's no class on Monday, right? It's Martin Luther King holiday. So don't come to class on Monday. And I'll meet you again in a week and we'll have lots of questions by then, right? So those are two methods for solids of revolution, washers and disks. Once in a while, you get a really difficult integral doing those, though. So they're not cure-alls, right? You know, you can't do every integral. Some of them are just too hard. Sometimes it's nice to have an alternative method, and there is an alternative. And that's, we'll say, another method for solids of revolution that sometimes gives you an easier integral, depending on the functions. Is the method of cylinders. This one I probably won't have time for examples tonight, so I'll give you homework on the three we did, the method of cross sections and the special cases method of discs and method of washers. And this time, this one I'll have the formula for you. Next time we'll do the example. So work up the formula this time and say it'll give us another method, right? And it looks like this. Suppose I have say a region like this, and I revolve this kind of a region that's below y equals f of x and above the x-axis, so it's this kind of a plane region between x equals a and x equals b. And suppose I revolve that around the y-axis. So I generate a solid that looks like this. Copy of this on the other side. Let's be minus b and minus a. All this around, I create the solid this way. Right? So this plane region is revolved to create this kind of vase, sort of. I mean, it's a cylinder on the outside, right? And it's hollowed out like here, so you can put a dirt and a plant in it or something, and maybe it's got a hole in the bottom for drainage. You could use the method of washers, right? You could take washers perpendicular to the y-axis and you get one formula, but there's an alternative for this. You can fill it up with cylinders. Instead of using washers, you could consider this. What if I try to fill the region like this? I partition the axis between A and B to go from x0 to xn into n subintervals. x1, x2, xn minus 1, xn. This is why you did that stuff in Calculus 1 where you partitioned it, because you needed to see why these formulas work, to be able to know when these work. So I'm going to partition the x-axis into n subintervals. X0 to xn will be the points, n plus 1 points, n intervals. And on each interval, I'm going to do this. I'm going to take and construct this kind of a figure, a big ring. What in the world is the volume of this ring if its thickness is delta x1 being x1 minus x0, the width of the first interval, and its inside radius here is this one, and its outside radius is this one, right? Well, we know the area of the washer, and then we just have to multiply it by the thickness here. So the volume of this one, the volume of the first subsolid here is the thick, let's see, the height of the washer. I can take the height of the washer at an arbitrary point here, x1 star. Just to be clearer. The inside ring looks like this. And it goes from x1 to x2 with a width delta x1. And then at some point along the x-axis, you get the height of this by taking the curve at a point x1 star. So the height of the cylinder is the function y equals f of x, this one, at x1 star. So that's the thickness. Then the volume of this thing is the area of this washer. It's room here, unfortunately. So the volume one is pi times the outside radius squared, which is x1 squared minus the inside radius squared, x0 squared, right? So outside radius x1 minus inside radius x0. The area of the disk is pi r squared outside radius minus pi r squared inside radius. That's the area of the washer here, and then you multiply it by the thickness, f of x1 star, and how high it is, right? Now we can rewrite that as pi times x1 plus x0 times x1 minus x0, f of x1 star, right? So that's the volume of the first ring in there. But wait a minute, x1 minus x0 is just delta x1, right? And furthermore, this one can also be written as twice x1 plus x0 over 2. Why would I want to do that? F of x1 star delta x1. So this is just this. This is this, and the pi's out front. So same formula. I just wrote it 2 times a half here and rearranged the order on the end. Well, this is the radius at some intermediate point. If I make my intermediate point x1 star, the point halfway between x0 and x1, and this one also the point halfway between x0 and x1, then this becomes I'll rearrange the orders here and call it 2 pi x1 star f of x1 star delta x1. Choosing x1 star equals the midpoint halfway through the interval. That's it. Similarly, the kth volume, VK, if we want to fill this with little thickened cylinders like this, so now I'll put another cylinder here with a hole cut out in the middle, and another cylinder here with a hole cut out in the middle, and I'll fill this things up with approximate cylinders. Finally, I'll get a thickened cylinder here on the outside, and I fill it up with cylinders, hence it's the method of cylinders, where the height of it with the same kind of construction. VK, the K cylinder has volume 2 pi xk star, f of xk star, delta xk, and we can say, I'm running out of time, I'll do this quick. The exact volume, if this is a continuous function, or f of x continuous, you can argue by underestimates and overestimates again. And since you always get the same number for a continuous function, but the volume can be called the limit as k goes to infinity of this sum, 2 pi xk star f of xk star delta xk should be the volume, the exact volume, k equals 1 to n. We use n rings, or n cylinders, thickened. But what's that? By definition, that's the definite interval of whatever function this is, right? Limit sum at a function, delta xk is the definite interval of that function. By definition of definite interval, this is the integral from a to b, the partition you made, of 2 pi xk star gets replaced with x. When you rewrite this integral formula will mean this if you replace xk star with x and delta x with dx. This formula means this by our definition of definite interval. There's the method of cylinders. So next time we'll do problems using this formula. I thought tonight I could at least derive it. Sometimes this integral formula is easier than using washers or discs. So try these homework problems. 13.2, there won't be any cylinders on it. We haven't done those yet, but this will be volumes by cross sections, discs, and washers. We've got 1 to 17 odd and 23. All right, and wait a minute. I'm sorry, I picked up my wrong paper again. We're on chapter 13. We're in chapter 5, 5.2, 1 to 7 odd. That's all right, I picked up your paper for their class. 1 to 7 odd, 11, 13, 19, 35, 41, and 43. And we already did 41, which is one of the harder ones. So try those and bring questions for next time, all right? Thank you for coming in. I'm sorry, just a tiny bit late, but at least I got the formula finished this way. Thank you online for coming in. I'm not collecting homework. I don't want to pass papers back and forth.